Hey AP Physics folks, this is Mr. Everly once again. Yet another video. We're reaching the end of chapter 28 here. I really encourage you to keep reading those sections and reread them. This video deals with something that occurs in your textbook on section 28-7, and that's forces on current carrying wires. Because when a wire has a current, that means there's charges flowing through it. If there's charges flowing through it, that means there's charges in motion. And if there is a magnetic field nearby, that magnetic field will exert a force on the wire because of those flowing charges. So here's the scenario here. And as you're taking notes, this is called forces on current carrying wires. And so I need you to imagine a wire with a current flowing through it in this direction. Call it current I. We'll bathe this wire in a magnetic field. Imagine that magnetic field is pointed in. I beg your pardon, this is coming out of the page because we're looking at the tips of these arrows. So imagine the arrowhead is kind of like a cone, and we're looking at the tip of the cone as the magnetic field is coming up out of the page. Now, we know that for a single charge passing through, and before I continue, remember, we know that this is electrons moving this way. We're talking conventional current. So we have to, like physicists of old, imagine positive charges moving up toward the top of the page when we know it's electrons moving down to the bottom of the page. It really doesn't matter. I just want you to realize that I'm treating these as positive charges moving through the wire. We know that a single charge in a magnetic field feels the force F equals QV cross B, where V is the velocity of the charged object, Q is its charge, B is the magnetic field. It's a cross product. And when this guy is sitting in the field and we have positive charges moving this way, using the right-hand rule, we can figure out the direction of the force. So the direction of the force on this guy, if we put our fingers of our right hand pointing in the direction the charges are moving, allow the fingers to bend into the direction of the magnetic field. I can't do it this way. I have to turn my hand over, and I can bend my fingers into the direction out of the page, which is the direction of the magnetic field given here. That means the force on this wire is this way. The wire will actually feel a force. If the wire is loose, it can get moved over by the field. Okay. Next, to find the force on this wire, we don't want to look at individual charges moving through the wire. We want to look at the current. Now, this would be the drift velocity of our little charge carriers. Now, drift velocity, just like any velocity, is going to be the length of the wire divided by the time it takes the charge to move the length of the wire. So we've got another variable in here. If I slip that into the equation, I've got QL over delta T crossed with B. Now, in order to keep this quantity a vector, I have to make L a vector. So L is just a vector that points in the direction of the current. Okay? Otherwise, we can't have a cross product. We can't have a cross product if one of the terms is not a vector. Now, very simply, the rate at which the current flows through the wire, so here's the charge per unit time going through the wire, is called current. So we come up with a brand new equation, very simply, that says that the force on the wire is IL cross B, or the current times the length, crossed with the magnetic field. Okay? So, an example. Very simple one. Imagine that we have a wire that carries a current of 8 amps. The wire is 3 meters long, or we're going to look at a 3-meter segment of the wire. It's sitting in a B field, and that B field is 50 degrees to the direction of the current. So this angle right here is 50.0 degrees. The length of the wire, 3 meters. The current, 8 amps. Okay? Magnitude and direction of the magnetic force. The force is IL cross B. That is ILB times the sine of the angle between L and B. So this becomes rather simple. We've got 8 amps of current. We've got a length of 3 meters. We have a B field of 400 milliteslas. Forgot to write that down. So milli is 1, 2, 3, so we'll say 0.400 teslas. Multiply by the sine of 50 degrees so that we get our vectors right. And if we punch that out, it turns out to be 7.35 newtons of force. So if I didn't press the wrong button on my calculator somewhere, you can check me. I think it's 7.35 newtons of force. Next question. What's the direction of that force? Okay, this is a cross product. So that means we're going to put our fingers in the direction of this vector, let them curl in the direction of this vector, and our thumb will point the way to the answer. So, again, current is this way. The magnetic field points this way. Okay, current this way. Magnetic field points this way. The only way I can bend my fingers into the direction of the magnetic field is if my thumb points out of the page. So we can say it's the positive K hat direction, or we could say out of the page works for me. Okay, so this wire sitting in the magnetic field feels a force of 7.35 newtons up out of the page. Okay, well, this is just a curiosity. What good is it? Well, it turns out this has huge practical applications. So let me switch to the force on a loop of wire. So imagine we've got a magnetic field into the page. Okay, so I'm showing that by X's indicating the direction of the magnetic field. If we put a loop of wire in the field, okay, so I've got this loop. Okay, not quite square, so we'll say this side is length A, this side has length B. Okay, and let's say we put a current in this loop. Okay, we'll have a current going clockwise, let's say. So here's the current I, current I, current I, and current I. Okay. Now, because these are current carrying wire segments in a magnetic field, they're going to feel forces. So what's the direction of the force? Okay, for the top segment, current that way, magnetic field that way, means we've got a force pointed straight up. This guy, current this way, magnetic field this way, force straight out. You can convince yourself that on this segment here, there's a force straight down. And on this segment here, there's a force out this way. Now, because this current is the same as this current, this length is the same as this length, this force will be the same as this force. They're both sitting in the same magnetic field. Same thing here. These two forces will balance. So on this loop, all the forces are balanced. Nothing amazing is happening at all. Unless we take this loop and we rotate it with respect to the field. So that's why I got this crazy red loop here. Imagine I take this thing and I pull the top toward you, toward the camera, and the bottom away from the camera. It's now sitting in a field which will balance forces on the sides here, and in fact balance the forces up and down, but there's going to be a torque on it. It's going to want to turn slightly in the field due to the presence of those forces. So to make that clear, what I'm going to do is draw a side view of this. Okay, we've got magnetic field into the page, and we're tilting the top of the loop a little bit out of the page. So get a clean sheet of paper here. Here's our magnetic field that was into the page. Okay, so we were looking at it over here. Here's our eyes. We're looking in this direction. Our loop now is tilted with respect to the field. Okay. The force F1 points this way. The force F2 now points this way. And I'm going to pivot this loop at the center. Now, of course, there's a force coming out of the page. That's this guy. There's a force going into the page. That's this guy, but they balance out. Okay, so I got F1, F3. Oops, I apologize. Call him F3. And they're going to cause, if we tilt this thing, it's going to try to torque this loop back to an upright position. Okay? So, how big is that torque? Well, the length of this side, remember, is B. So that means the length from here to our pivot point is B over 2. The angle of the area of this field, the area of this loop, with respect to the field, let's call it theta. So I can find the torque that this force exerts on here by taking the component of B2, which is perpendicular to F. So I've got a couple of options. I could take the component of F perpendicular to B2, either way. But if I draw my little triangle here, you would probably agree that this is angle theta, and this side is B2 times the sine of theta. Okay, so in other words, I got a force, and it's located a perpendicular distance of B2 sine theta away from the pivot point. So that means the torque created by that force, R cross F, is going to be B over 2 sine theta times F1. Okay? Same analysis down here. The torque created by F3 is going to be B over 2 sine of theta times F3. Okay? So both of these torques are in the same direction. They're both trying to twist this loop back to an upright position. So that means the sum of the torques, if I add them up, I've got the same force, same magnitude of force, the same angle, the same B over 2. I'm just going to say it's 2 times B over 2 times the sine of theta times the force on our loop. Okay? So that means we've got B times F times the sine of theta as the sum of the torques on this thing. Okay? So remember, the force on this is IL cross B. Okay? Now, the force is on the wire that is perpendicular to the page here. This is, again, this guy of length A. So there's a current I going through him. He has a length A, and the B field is B. We'll use capital B. The wire is perpendicular to the field, so I'm going to lose the sign of theta. So I'm going to say each of those forces is IAB. So check it out. The force here, I've got B times IAB, where capital B is the B field, times the sine of theta. So this represents the force, the current, times the length of the wire, times the magnetic field. I've got the length here, B, and I've got the sine of theta. Okay. So I'll rearrange this slightly. I'm going to say B times A. B times A is actually the area of my loop. So I'm going to say it's the current times the area of the loop times the B field times the sine of theta. Okay, so this little guy is area. All right, I need a little room here. Okay. Now, one more thing. Let n equal the number of windings, number of loops. So in other words, our loop doesn't have to be made of one wire. We could loop many, many, many wires around and increase the amount of force. So the torque now is going to be N times I times A times the B field. Okay, all I did was stick an N in here, times the sine of theta. Okay. This represents the properties of the coil. It tells us how many loops the coil has, how much current is going through it, and what the area of the coil is. This, of course, is the magnetic field the coil is sitting in, and theta is the angle between the perpendicular to the coil and the magnetic field. Remember, that's this guy here. Okay. Sometimes they call this quantity here the magnetic moment of the coil. It's Greek letter mu. We use mu for a lot of things. And so if the torque is equal to mu times B times the sine of theta, I'm going to say that the torque is a vector, mu cross B. Okay? Which is kind of pretty, but practically speaking, this is the equation we need. Okay? So, finally, why do we care? Well, if you take a loop of wire and you put it in a magnetic field and you add a little bit of current, it wants to turn. Okay, so imagine that at the moment we do this, we switch the direction so he continues to turn. If he goes beyond, if the inertia takes him beyond, he's going to want to flip back up. What if at the moment that inertia takes him beyond, we switch the direction of the current in the loop and creates a torque in the other direction, switch the direction of the current, creates a torque in this direction, switch the direction of the current, creates a torque in this direction, and we can make this thing continue to spin. What we have here is an electric motor. So an electric motor will spin in a magnetic field. Why? Because we put a current through the windings, we put a current through the loop of wire. Sitting in the magnetic field creates a torque to turn the wire. As soon as it gets beyond 180 degrees, we flip the current and get it to sweep, continue the sweep back up, flip the current, and so on. So we can make this winding spin for as long as we want, as long as we've got current to put through the wire. We set it in a magnetic field usually created by permanent magnets, and what we have is an electric motor. Okay? Electric motor, all it is, here's an example. All this guy is a bunch of magnets inside, and here are the copper loops. They're looped around with lots and lots of coils so that this thing will spin in a magnetic field. Now, one example that we could do, a mathematical example of the force on the loop, or I beg your pardon, the torque on the loop, is this little guy. So imagine we've got a loop of wire that we're sending a current through, and that current is 5 amps. The radius, 2 centimeters, or 0.020 meters. Uniform field is 0.060 teslas at an angle of 30 degrees to the loop. Okay, so if we could see this from the side, we'd see that the field and the loop have an angle. So here's the loop, let's say from the side. Here's the area vector, so right from the center of the loop we put a perpendicular out, and this is the magnetic field direction. So we'd say, okay, here's 30 degrees between the perpendicular to the loop and the magnetic field. Okay. All right. So we know the torque on this guy is mu cross B, or much easier to deal with is NIB times the sine of theta, the angle here between mu and B. And I forgot the current, sorry about that. So it's NIA B times the sine of theta. Excuse me, I didn't forget the current, I forgot the area. So the number of loops times the current times the area of the loop times the B field times the angle between the B field and the perpendicular to the loop. Okay, how many loops? We have just one. The current, according to the problem, 5 amps. The area, this is a circle with a radius of 0.020 meters, so we'll do a pi r squared. The B field, 0.060 teslas, times the sine of 30 degrees. Okay, so our job is to punch that out, and we end up with an answer of 1.9 times 10 to the negative 4 Newton meters of torque. Okay, so the B field wants to pull that thing back up into a right angle to the field, or make this guy perpendicular to the field, then the forces will balance and there'll be no torque. All right, so at this point, at 30 degrees, it feels a torque of 1.9 times 10 to the negative 4 Newton meters.